First of all, I thank the organizers of this conference, the 5th International Conference of Virtual Reality, for inviting me to give a presentation on modeling of monkeypox and COVID-19 model in the context of fractional numerical stochastic with Lugard function. So I'll start my presentation by just showing my profile. I'm the Acting Director of Research, International Program, and Institutional Advancement of my university, that is Akinta Piaminka, University of Skills Training and Entrepreneurial Development, which is situated in Ghana. Now, this is the outline of my talk. In the talk, I'll talk about introduction of my study. We're going to talk about mathematics modeling formulation. I'm going to talk about dynamical behavior of the co-infection model. I'll also give a brief overview about the existing uniqueness of the solution. I'll try to present numerical scheme and then associated results, and also share some conclusion out of the talk. Now, way of introduction. See that the history of the monkeypox virus begins with a small pox-like outbreak in 2 cynomolgus monkey, which were sent from Singapore and Copenhagen in 1958. Then during the next 10 years, in other words, after 10 years of this outbreak, these were, monkeys were, some monkeys identified in the United States now begin to have this disease. But the fortunate thing was that they did not transfer or transmit the disease from these monkey species to human. That's the good news at that time. But I want to share with you that the first case of monkeypox in human was detected in 1970 in Democratic Republic of Congo, which is in Africa. I want to also let you note that Democratic Republic of Congo has River Congo, which is one of the biggest rivers in the world. And it's also interesting to know that that is where Ebola in Africa also started from. So maybe ecologically, there's something there that researchers need to look at it. Very interesting. So monkeypox disease can occur through animal to human, or infected human can also infect human. In some part of the people eat wild animal, especially in Africa. A lot of people try to eat wild animal. This is zoonotic relationship. So when people eat this animal and then they carry this virus or harbor these viruses, but they are not harmed to their host. But because of climate change, the genetic makeup of some of these viruses have changed, and therefore causing a lot of threat in human society. Really, the disease can lead to pneumonia, encephalitis, or eye infection. Monkeypox mortality rate has ranged between 3 to 6% recently, and this is serious. Even 0.5% is serious. And I call on WHO to take serious steps in helping addressing some of these normally we call tropical neglected diseases. They are necessary because they are affecting the developing countries as well. So human monkeypox is zoonotic, as I already said, that is transmitting disease from animal to man. Human typically contract monkeypox from rodent. Like I said, in some part of the world, if you go to China, they also eat a lot of wild animals. The animal like rodent, pets. When you get contact with them, they harbor these viruses. You are likely to get infected. Like I was already talk about the effect of climate on some of this genetic makeup of these viruses. So also look at coronavirus, which is common. I'm sure some of my participants might have even infected with COVID-19 one way or the other. It's not common. I remember in 2020, the menace that befallen on the whole world, where WHO has to upgrade it to pandemic instead of endemic. That shows the threat that caused the society. And the economic meltdown that this disease caused the world has still not been recovered. So coronavirus is a virus-borne disease infection caused by SARS-CoV viral. And SARS has been there for so many years. So when COVID came up, people said that it's SARS. Later, research showed that the variation is a bit different, but they have a lot of commonalities. So COVID SARS-2 is an RNA virus and belongs to family called coronavirus. Most patients infected with this virus will have mild, sometimes severe. Some may, of course, symptomatic. They have it, they don't even know they have it. For people over the age of 65, normally when people get older, getting older and older, they have what you call chronic diseases. You call underlying health. So if somebody has, let's say, kidney or liver issue or diabetes and so on, so these people, they become very prone to this disease. And therefore, if special care are not taken, some of them are likely to even to lose their life with little, attack from COVID. So symptoms of COVID-19 may emerge within 2 to 14. That's the incubation period of the virus exposure. That's why sometimes we try to quarantine people when we are exposed to the disease. Now, ladies and gentlemen, I also want to share something on the co-infection. Co-infection means one species having two diseases at the same time. And this is sometimes very, very serious. It is sometimes very, very, very serious because even harboring one disease could threaten the individual's existence or survival, let alone having two diseases at the same time. So understanding the dynamics of co-infection is critical for healthcare planning, decision taking, so that public health in every country can make adequate preparation towards any eventualities. Now, I come to why mathematics is important in this enterprise. We say that mathematical models have been frequently utilized to simulate and understand the dynamics of many infectious diseases. And this is very important because when even COVID came, let's ask ourselves, how many, the developed countries had access to ready-made data? It took a while to compile data for us to, look at the genetic makeup, sequencing of the virus to determine the variations that later came up. And one tool to help us to do when such situation arises is modeling, which is mathematics. Or sometimes, if we have the tools, we must also think about cost-benefit analysis. So mathematical model will give us an overview, will give us a gist, will give us some kind of knowledge in theoretical realm, which can be practicalized and take decision in going forward. So mathematical model enabled investigation of various scenarios and intervention options without the need of costly, like I already mentioned. I don't need to go to the lab to spend a couple million of theories to gather data to do same that I could have done when I have my parameters available just to do my simulations. Sometimes you need also real life data to generate some bit of data parameters in order to do proper simulation. And that's still less costly than a typical life sciences laboratory work. Now, why did I not choose deterministic approach, but rather I decided to use what you call fractional calculus? Here, I'm trying to say that the fractional calculus concept utilizes the notion of differentiation and integration in the context of non-integer perspective. For example, if I integrate half or 1/3, 1/5, 1/6, then it means, or if I differentiate in that context, it means I'm doing fractional derivative, which is very important. You understand me very soon. So why not determine? The reason is that fractional calculus concept is embedded in what we call hereditary and memory effect. In other words, in order to simulate, it usually try to make use of the past event or history. Then it takes into consideration the present circumstance with which the system or the model finds itself to predict future. And let me bring this in reality. In any or every human endeavor, if you know your history, if you know your present condition, you become very careful what to do in your future. And therefore, predictions are deemed likely to be accurate compared to, the deterministic which have been doing in the past. And also, better estimation of parameter values. From my studies for the past 2 years, I've emerged that in simulating fractional derivative context, it uses smaller parameter values and even smaller initial conditions. So if you quantify it in reality, it means the amount of resources even required to predict same output is lesser in the fractional context compared to what we call the classical, or people call it deterministic world. Okay. Then you also have what you call the crossover behavior. In other words, the tail of this kernel. For example, we have what you call Mittag-Leffler function. Which is we normally generally call it the general Mittag-Leffler function, which was prepared by Atangana Belenu. So they call it ABC operator. Then we also have what we call Capito-Fabrizio operator, which also in terms of the generalization also based on exponential function. Then also have what you call Capito operator, which is also based on what you call power law. So the Atangana-Belenu operator, with the generalized Mittag-Leffler function, is able to stretch the tail of the kernel, moving from one operator to one another, stretching the tail to one another, making it more accurate, predictable than the other two, operators that I've just mentioned. And then when also come to even data fitting, it has emerged from studies by Ella that it fits better in fractional derivative perspective or calculus than that of a classical. Now, in this study, I try also to embed it or include stochastic component. Let me also talk about this a bit. It is a fact that when it comes to infectious disease, it is not easy to predict, irrespective how advanced a country is. When COVID came, we all saw how in advanced countries, a lot of people lost their life. They have all infrastructure, medical infrastructure, health infrastructure that you may think of. But did they survive? So it is difficult to predict the number of infection at the next 1 hour, 2 hours. So to mimic that effect, this work also incorporated stochastic component to depict that effect. So we have some random fluctuation in the model to show that at time t, time x, the disease infection rate could go up, could go down, depending on other factors like climatic condition and others. So now I come to the model itself. The model is formulated based on the dynamics of monkeypox and COVID-19. Why are we saying this? Because we are putting these diseases together as one composite. So I'm saying that the total human population, which is N of age, is partitioned into the following. So in this model, we have the following sub compartments: susceptible individuals, infected individuals with monkeypox, infected individual with COVID-19 IC, infected individual with both. That's what you call the co-infected, the individual having the two diseases at the same time. The individual recovered from monkeypox RM, individual recovered from COVID RC, individual recovered from both with RMC, and the susceptible rodent RS, and then infected rodent. Okay? So this is the model description for my study. So based on the description, I came out with the following non-linear fractionalized system of equation in the context of generalized Mittag-Leffler function, which is better known as Atangana Veleno operator in the Capito sense. So I obtained the following systems of equations. I can explain a few of them for the purpose of time. For example, equation, the system, the first equation, which is susceptible human. Then this big omega sub H tells you the recruitment rate through migration, through birth coming to the system. There's the individuals, the rate A1 is the rate at which individual recovered from monkeypox, loses their immunity and becomes susceptible in the system again. A2, also individuals who have also recovered from COVID, but naturally you can't recover from COVID throughout your life. You lose the immunity, you become susceptible again. So you join those people joining the susceptible class. Similarly, A3, the individual recovered from both disease, losing the immunity of being recovered from the two disease, coming back into the system. And then this one is also force of infection, which I've defined, I'll show you later, with respect to monkeypox, the force infection with respect to COVID. And this is natural mortality rate. Whether you have the disease or not, naturally, human beings are subject to die. You can die naturally. So we've taken that into consideration. And then, so let me take out, so this equation 2 is also has to do with human being infected with monkey. So force of infection interacting with susceptible human being. There's also force infection of COVID interaction of what infected what? Monkey. And this is gamma, individual recovered, joining the recovered from monkeypox. This is also representing natural, this is what they call disease-induced death. People dying out of, infected with monkeypox. Remember in the introduction, I said that the mortality rate ranges from 3% to that of 6%. And this take of their natural mortality rate. Similarly, that can be also observed in the COVID perspective. So this one also has to do with force of infection due to COVID, force of infection due to monkeypox, interaction with people who have infected with monkeypox. These are also gamma 2 is also represented by the individual who have recovered from the COVID-19. So they join the recovery compartment here. People also die out of COVID, and this also natural death. Then this compartment also represents those who have the disease at the same time, called a co-infected compartment. So individual force of infection, okay, respect to COVID, interact with people who have COVID, force infection with monkeypox, interact with people who have this in people who have monkeypox, sorry. In the first infection of monkeypox, interact with people who are infected with what? COVID-19. And as usual, this natural mortality rate. Okay, and then this theta also represent those who recover from both diseases we see over here. So the rest are respective individuals who recovery for COVID, recovery from both disease, is recovery from monkeypox. And then let me talk about these two compartments, which are not human beings. This will represent the rodent. So societal rodent through birth, through migration, coming to join that community in the forest or a particular area. This also force infection, interaction with susceptible rodent. This also rodent dying naturally. And then this is a force of infection, interaction with susceptible COVID. Then this one, people who have the infected with the COVID, the rodent, the animal rodent infected with the COVID in the forest or in the community, they find themselves dying naturally without being or due to, the infection. So remember, I told you the first infection. So first infection for monkeypox, this is beta subscript M. This is individual rodents infected. This is human infected. This human infected with both disease. So if susceptible human interact with any of these compartments, they get infected and they have what? Monkeypox. Then you come to COVID. First infection is this. So individual human being interact with people who have COVID or people who have both the disease, you get COVID. In other words, susceptible individual interacting with them. Then the rodents, susceptible rodent interact with rodent which are the monkeypox, or individual who has both monkeypox and that of COVID. If the rodent interact with the individual human being, the rodent also get infected. So that does it for the explanation of the model. Okay. So I move to the analysis. In order not to bore, my audience with rigorous computations, I decide not to bring all this computation here for the purpose of most of my audience may not be in this kind of business. However, I still want to share what actually happened in the actual work. So here I said that fixed point theory was used to establish the existence and the uniqueness of the solution of the co-infected model. Because I'm doing fractional derivative model, I must be able to establish that if I don't look at the stability analysis of the system, does the solution exist? Does it have a unique solution or multiple solution? So I used fixed point theory to prove, which showed that it existed. Then these are also basic stuff we do in every epidemiological studies. Causativity of invariant region was also examined. Then we also want to show that every parameters that were used for this study was not negative. We did that. Now, this is also very important in every epidemiological analysis. You want to see if there's no disease in the system, does it have a solution, equilibrium-free solution? So we make that this is the equilibrium solution. This is susceptible is also the susceptible region. The rest are 0, 0 in the compartment. So you can see as is shown here. Now we also look at reproductive number. One of the very critical ingredients in mathematical modeling of infectious disease. This is the threshold that shows us one infectious individual, how many can he infect in a virgin population, which we call the susceptible population. And this has been realigned based on, remember, we are talking about COVID, we are talking about monkeypox, we are talking about what? The co-infection society. We are talking about rodent, monkey, and the COVID. 3 species are being talked about. So in the realm of the reproductive number, I try to segregate, not to composite them, for you to understand what is happening here. So the first one, you can see that reproductive number 1 is dealing with the monkeypox infection. So here we mean that if you have one individual who has monkeypox, how can he infect, or how many is it possible for him or her to infect other susceptible in the community? That's for this. This is the rate. Similarly, this is also for COVID, the rate at which individual will get COVID in the community. This is also for rodents, the animal, the rate at which one infected rodent can infect the number of, virgin or susceptible rodents in the community. Then I try to play around a bit of maths. I said, okay, let me look at stability or disease-free equilibrium. And I try to use Jacobian matrix, just establish this to show that the system is locally stable under this condition. Okay. Then I come to very interesting component of my work. Now I try to incorporate the stochastic component. And then this eta 1, eta 2, eta up to eta 9 represent the stochastic constant that were used in the simulation. This showing the Brownian motion, K1, K2, K3. This is called the Brownian. I use the Brownian motion. So this represents the Brownian motion. So this has been transformed into what you call stochastic fractional model. So in the stochastic constant, I'm going to assign some values in the simulation in order to show me what you call the randomness or the fluctuations that will come up in the analysis. So the equation here that we see here, I want to retransform the equation to make it simpler for me to work. So I reorganize this equation in this form nicely, very nice. Then, based on that, I try to use the Newton polynomial, which is constructed in the perspective of Mittag-Leffler function. In other words, Newton polynomial numerical scheme has been coded and embedded in the Mittag-Leffler function, which better people call the AB Satangana Boolean operator in the capital sense. So each of the compartments were coded. The numerical scheme were written for it. So this is for susceptible. This is for the monkeypox scheme. So all of them, you can see I did all of them. So this is the scheme which were implemented in MATLAB. So I'll define this. After that, these were parameters that were used. I tried to estimate these parameters for my experiment. So from the experiment that I did, I tried to estimate these parameters, and they were nice. So I used the eta symbol that I show you. I used stochastic constant to be called 0.04, and these were results that were observed. And I'll quickly explain these results quickly to you, ladies and gentlemen. Now you can see this is susceptible individuals in the community. And you can see the fluctuation, the randomness. And you can see that the green depicts this omega depicts 0.6. So you see 0.6, you move to 0.7, so we move to 1. So what is therefore showing here is that at the fractional order, this is what you call the fractional order. So the fractional order 0.6 increasing to 0.7, increasing 0. What is happening? You see that the number of susceptible individuals in this compartment are what? Reducing. And this is typically what is expected in a epidemiological model, all things being what? Equal. Because the number of susceptible are being reduced. They are moving away, they are getting infected. When people are getting infected, then they lose their status, become susceptible, they move to what? Infectious what? Compartment or exposed compartment, depending on the compartmental model that we are dealing with. And you can also see clearly that there's some kind of fluctuations in the system. Now, if you look at individual human being infected with monkeypox, you can also clearly see that as the fractional order going up, the number of individuals infected also going up. So one can infer typically that in this particular simulation, it appears that a lot of people are getting infection of the monkeypox, and they are moving towards this compartment in real life input. Okay? Now let's also look at what is happening in the human compartment, those who have the COVID. And the situation is the opposite here. What's happening here is that as the fractional order moving from 0.6 to towards 1, rather the number of people getting infected are reducing. It is possible. Because if you look at what is happening in reality now we know COVID. But I myself, epidemiologist, mathematical biologist, I know a bit about monkeypox, but I didn't know we were going to have an increase in this disease recently. Except that in just last 2 years, for example, in my country, Ghana, it also became an issue where government issued order that people going to airport, they have to test whether they have it or not. But we thank God that, or Allah, that thankfully the situation has changed. Now we come to the situation where both of them have it. We can say that in the intervention from the first 6 days, let's see what is happening. Very interesting. It is showing that as the number of people, getting infection increase, the fractional order also increasing. However, after 8 days going, the trend begin to change. And what happens is that, and you can see a lot of fluctuations, highly uncertainty are happening here. And if you are a manager and a public health officer, it will be difficult for you to predict what's likely to happen. A very interesting simulation here. So from this 8 or 7 day going, the reverse happened. What was happening is that as the fractional order now increasing, the number of people getting the disease are also what? Reducing. Okay? Okay, so let me continue on with my explanation here. And this is recovery from monkeypox, and also showing here that as the fractional order derivative increasing from 0.6, 0.7, 0.7, 0.85 towards 1, the number of people recovering are also what? Increasing. That's very good for society. It means we are curtailing resources available, right? Both human resource and material available to help us to increase through maybe medication or any other means. Now, similarly, the case is also no different from what is happening in the COVID perspective of the co-infected model. You can also observe that as the fractional order increasing, the more people also recovering from the diseases are also high. Now, this is where it makes very interesting dynamics. This is both recovered from the disease. And this is highly random or fluctuations, randomized or fluctuations. It is difficult to tell what is happening here. But we can see in the general trend that the graph is not straightforward as it is, but you can see a lot of fluctuation, randomness. So as a planner, health planner, it beheld on you to not take anything for granted. It's like winter. Within a day, sometimes the temperature improves. After 2 or 3 hours, it can drop, and so forth. So this telling you that when such a situation happens, the health authorities should make contingent measures to curtail any unplanned eventualities in society. Okay, this is also for the reading. So this is also situation where the susceptible reading as the fractional order is increasing, the number of reading also, also um, also decreasing. And this is normally expected from any epidemiology because more of them are moving to this one. Now, again, this is also a situation you can see that the green is the 0.5. So as it's increasing up to, I think, the A day, then the situation become reverse. So in this case, you cannot predict entirely, so it's going to be same throughout. Then the reverse started. So health authority must take note. So I also tried to simulate with that stochastic. And the explanation is not different from what I've explained, except that in the stochastic component, you see fluctuations, moving up, moving down, moving up, moving down. Otherwise, they are very, very similar. So I don't know much to say here, except I'm saying that the difference is that this one is also fractionalized simulation. However, I'm not showing the fluctuation. This is more like linear kind of straightforward, but in a real life situation, when you talk of epidemiology, or when you are looking at epidemiology, it is not the case. It's not the case. So I don't want to waste my time here. It is the same, except that the other one I'm showing the fluctuation. This one I'm not showing the fluctuation, but it's the same, except that the stochastic component are not part in this simulation. Okay. So having said this, I want to draw some conclusions from my talk. This work investigated a monkeypox COVID-19 model, fractionalized mathematical model of stochastic component. I've shown that, haven't I? Have. Also said that this work utilizes well-known mathematical function called generalized mathematical function. And one of the characteristics that this operator has is what the ability to cross over from one operator to one another. The tail can stretch so much to enter another domain. That make it more accurate. We also look at the basic properties. Remember, I show you some basic properties. In fact, I didn't put them here, but I've done it in the work. But at least I show you the reproductive number, also explain to you the implication of the reproductive number in my talk. Then the dynamic behavior of the model was, remember, I show you the local stability, Jacobian matrix, and concluded that it's stable. Then I also did say again in my talk that in order, sometimes we decide not to look at the stochastic, look at the dynamical behavior of the model, but I could just also study the uniqueness and existence of solution, which is okay. In this work, I did, but I didn't show here to bother my audience with all these mathematical, computations. But I did also mention that I use what you call fixed point theory to do that. Then I also again mentioned or stated that this work the simulation was also based on the Newton polynomial was used, which is embedded in multiplicar generalized function, not a classical Newton or deterministic Newton polynomial. But Newton polynomial, which have been infused with a Tangen-Belloni operator, or what you call the generalized with legal function. Then I've also shown you numerical simulation results to support what I've just talked about. And for example, further simulation on the sum of the compartment based on the human infection rate indicate that as infection rate, remember we saw, for example, in the monkeypox human, as the human infection, as the fractional order increases, the human infection were increasing, and the societal compartment were rather reducing. Similarly, we also even observe in the rodent compartment, didn't we? And then even the recovery compartment, we saw that as fractional order increasing both for COVID and that of monkeypox, they were rather what? Also increasing, which is good. And then we said that the recovery compartment for co-infected compartment were so random fluctuations, difficult to predict whether there was increase or not. So therefore, proper strategy must be put in place to reduce interaction between infected individuals, because we have seen that there were high increasing in the simulation. So we can curtail parameters associated with these, especially the reproductive numbers, respective species that were put together for this co-infection, especially the denominator. So the graphs obtained for deterministic, so sometimes I call even though it's fractional, I call it fractional deterministic. The model with stochastic are similar. They look almost the same, except that the stochastic, I'm showing some fluctuations, showing that at time t, this can happen. It can go down like in the winter situation time. So monkeypox co-infection model can be investigated using concept of fractional fractal. So I'm just making recommendation. Same work, somebody can also look at this in the context of fractional fractal model, or these days people use what piecewise function, fractional piecewise function model, and so on and so forth. And these are some of the references that were consulted for this study. And thank you for listening. Allah bless all of us. Then I bring greetings of Ghana to you. Bye. Enjoy your day. These are some of the artifact symbols that you can find in Ghana. And then I also bring a big history of my university. And here I'm saying that my university was a part of an existing university, but an act was carved in August 2020 under an act named 2026 Act by the Republic of Ghana. And then this was like a college of existing university, which has two campuses now, Master Campus, and which deal with technology-related programs. And then the other campus is College of Agriculture, dealing with other agriculture-related programs. And I say thank you. And the thank you in my local, that is called Medamasi. Bye.